Vijay Shekhar sir. Hello. Am I audible, Vijay Shekhar sir? Good morning, sir. Chandrasekhar sir.
Very good morning, Sivareddy garu. Very good morning.
Good morning, sir.
Good morning, sir.
Good morning. Good morning.
శివారెడ్డి గారు వినిపిస్తుందా? నమస్తే సార్.
వినపడుతుంది సార్.
నమస్కారం.
ఓకే రైట్.
మీరు రెడీలో ఉన్నారు కదా సార్? విజయ్ శేఖర్
నేను రెడీయే.
విజయ్ శేఖర్ సార్. విజయ్ శేఖర్.
రెడీగానే ఉన్నాను.
ఓకే ఓకే ఓకే. సార్ ఫస్ట్ మీరు లీడ్ తీసుకోండి సార్, చంద్రశేఖర్ సార్.
తప్పకుండా అండి.
ఓకే సార్.
ఆయనకి వెల్కమ్ చెప్తాను.
సార్ 9:30కి స్టార్ట్ అవుతుంది సార్ ప్రోగ్రామ్. 9:30కి సార్.
అదే 9:15 అని ఉంటుంది కదా, అందుకనే
9:15 కాదు సార్, 9:30 సార్.
అదే ఆయన జాయిన్ అవ్వగానే నేను ఆయనతో ఇంటరాక్ట్ అవుతాను. అంటే జాయిన్ అవ్వగానే మనకి ఆయనకి వెల్కమ్ చెప్తాను, గీతంకి చెప్పి నేను ఎవరో చెప్తాను. జస్ట్ అబౌట్ గీతం 3 క్యాంపస్ మీరు ఆర్గనైజ్ చేస్తున్నారని చెప్పి మీకు నేను హ్యాండ్ ఓవర్ చేసేస్తాను
సార్. యాక్చువల్గా సార్ వచ్చినా సరే మీరు మాత్రం 9:20 స్టార్ట్ చేయండి సార్.
వచ్చినా కూడా మామూలుగా ఇంటరాక్ట్ అవుతుంది, ఆయనతో ఇంటరాక్ట్ అవ్వడం తప్పలే కదా. మనం అంటే ఆడియో వీడియో కరెక్ట్ గా ఉన్నాయా లేవా ఒకసారి చెక్ చేసి 9:25 నేను స్టార్ట్ చేస్తాను.
ఓకే సార్.
ఆయన వచ్చిన దాన్ని బట్టి చూద్దాం. వాళ్ళకి ఆఫ్టర్నూన్ అయిందేమో కదండి టైం, 1:30 ఎంతో. అదే న్యూజిలాండ్ లో 1:30 ఎంతో అయి ఉంటుంది ఆఫ్టర్నూన్.
Sir, Jason Legrow entered into the success in participant.
స్వామి గారు.
Sir,
ఓకే రైట్. అడ్మిట్ చేశారు కదా, రైట్.
Very good morning. Very good morning, Professor Jason Legrow.
Hi.
Hi. Very good morning.
Thank you.
Yeah, is my audio and video clear for you?
Yes, it's good.
Yeah, even yours also. A warm welcome to
Thank you.
Our university. The actual schedule starts at 9:25 Indian time.
Right.
So I'm very happy to see you.
Yes, I'm happy to be here. Thank you for having me.
Yeah. Because I gone through your profile. You've done your graduation from pure maths.
Yes.
And post-graduation is from optimization and combinatorics.
That's right.
Yeah, then you extended your PhD and then you completed your PhD, right?
Yes, that's right.
Yeah, excellent profile. Really, you are a role model to our research scholars.
Well, thank you very much.
Yeah, even these days we are marching towards the applications of the pure mathematics.
Yes, exactly.
Yeah, particularly the modern number theory and all. And really the work I gone through some of your papers also, your research work. We are in fact marching towards designing crypto systems using mathematical models, then analyzing analyzing the cryptanalysis. Yeah, the faculty and the scholars are eagerly waiting for that cryptanalysis, the part that you are going to deliver. Yeah, basically the GitHub campus is situated in 3 states in India.
Mhm.
Yeah, the first campus is in Visakhapatnam, that is just a side to seashore. And the second campus is in the Hyderabad. And the third campus is in the Bangalore.
Mhm.
Now the dynamic faculty of the Hyderabad campus are organizing this.
Yes.
Yeah, and I'm happy to say that I'm the senior most in the Geetham University in the Department of Mathematics. Yeah, I'm rendering my services since 1995. So it's
wow.
already, right. But still, I'm happy to be a student of yours today. You can see I'm the first participant. Yeah. Yes. This, I feel it as a privilege that I'm the senior most and I'm the first student. So you have to give me full marks as I'm a sincere student. So nice of you, Jason Legrow. Now, I think so. Exactly by 9:25 Indian time, we are planning to start this.
Mhm.
Yeah, what is the exact time in Auckland now? Right now?
Right now it's 3:51 p.m.
Oh, you had your lunch?
Yes.
Yeah, that's fine. So again, I will see you at the ending of your lecture, Professor. Now I'm handovering to my dynamic coordinators of this faculty development program. So the head of the department in the Hyderabad campus is Professor Maruti Prasad.
Mhm.
And the coordinator are Associate Professor Siva Reddy and Professor Narasimha Swami. They might have interacted with you regarding this. And on behalf of Geetham University, we heartfelt thanks to you for accepting this.
It's my pleasure. Thank you very much for having me here.
Yeah, yes. Sir, I request Dr. Shiva Reddy garu, please take over.
Sir, now we will play some promo, sir.
Yeah, yes, sir. You can watch.
Yes, sir.
Yes. We a video like AV clip of our university. Sir, go ahead, sir. Go ahead.
Okay, sir.
So it will be for hardly a couple of minutes. That's all. The AV.
Sure.
Good morning, Maheshwar Rao garu. Maheshwar Rao.
Hi, Jason. Sorry, sir.
Yeah, this is a good one. So I'm Jason Legrow. You can have interaction, sir. Now we are going to play AV.
Yeah. Jason, all the best. This is Maheshwara, I was a student.
Yes,
Right.
of course.
Yeah, thank you.
Thank you.
So, thank you for accepting this.
Of course. I'm glad to be here.
Good morning, Jason Legrow, sir.
Hi.
Hi, sir. I'm Dr. P. Narasimha Swami, coordinator for this program, sir.
Nice to meet you.
Thank you, sir. I'm friend of Maheshwara Valluri, sir. Thank you for accepting our invitation, sir.
Of course, of course.
Sir, we are going to play one promo which takes almost 3 to 4 minutes. After that, we will start, sir.
Sounds good.
Good morning, sir. Chandrasekhar, sir. Sorry.
Very, very good morning. You must not say sorry. Yes, sir.
I was talking with your friend about you yesterday, Dr. Sri Lakshmi.
Oh, Sri Lakshmi. Okay.
She's my friend.
Oh, your friend. But the world is too small. The world is too small.
All right. Okay.
Yeah. Yes. Yeah. I'll talk to you about that later, sir.
All right. So,
Yeah.
sure. Continue.
Sir, is there any problem with AV? Shiva Reddy, sir? Is there any problem?
Sir, 1 minute, sir. 1 minute, sir. We will play,
Yeah.
sir.
Yes.
We'll play, sir.
Okay. Oh, that's nice. Shiva Reddy garu, you can
Yes.
continue, sir.
A very good morning to all. Let us continue with the further sessions. Now, I would like to welcome Dr. Jason Legrow from the University of Auckland, New Zealand, to expound isogeny-based exotic signatures and their applications to blockchain. Now, I invite Dr. Vijay Shekhar, Associate Professor, Department of Mathematics, Geetham, Hyderabad, to introduce Dr. Jason Legrow from University of Auckland, New Zealand.
Okay. Thank you, Shiva Reddy garu. Very good morning, everyone. Very good morning, Jason Legrow. I am glad to introduce Dr. Jason Legrow to this 5-day ATAL faculty development program on impact of quantum computing on cryptography and blockchain technology. Dr. Jason Legrow obtained his Bachelor of Science in Pure Mathematics from Memorial University of Newfoundland in 2014. Dr. Jason completed his post-graduation in Computronics and Optimization in 2016. Dr. Johnson obtained his Doctor of Philosophy from the University of Auckland in 2020 with specialization quantum information. Presently, he is working as a research fellow at the University of Auckland. Dr. Johnson actually doing research on secure and efficient implementation of isogeny-based crypto systems and cryptanalysis of post-quantum science. My sincere thanks to coordinators of faculty development program for giving me a nice opportunity to introduce Dr. Jason to participants of FDP. Once again, thank you all.
Okay, now I request Dr. Jason Legrow to address the participants. So I hand
Hi,
over
everyone.
to Dr. Jason Legrow.
Hi.
Sir, now
Thanks,
you can
everyone,
start,
for thanks for. I'd like to share my screen, but I need to be made a co-host before I can do that.
1 minute.
Of course. While we're waiting, thank you, everyone, for having me. I'm delighted to be able to speak to you about something that I think is very interesting and important, for internet security going forward. It's a very important field, and it's sort of wide open with many things that need to be done.
Sir, now you share your PPTs.
Oh, sorry, just give me 1 second. I need to close some windows. There we go. There, can you all see my slides now?
Yeah, yes, can go ahead.
Excellent, thank you. So I'm going to be talking today about isogeny-based exotic signatures and their applications to blockchain. So before I get started on the material, I just want to acknowledge my many colleagues with whom I've been thinking about isogeny-based exotic signatures and blockchain applications. Primarily, these people are at universities in Australia and some in Malaysia. And without them, I wouldn't know most of what I know about isogeny-based exotic signatures and blockchain applications. So thank you for all of them. So let me quickly outline what the talk is going to be about. So in the first section, I'll talk about the fundamentals of signature schemes, sort of abstractly and at a low level. So this should be rather introductory. Then I'll start talking about what I call exotic signatures. And then in the second half, we'll start looking at isogeny-based cryptography in general, and in particular, the sort of underlying computational problems of isogeny-based cryptography. And then we'll talk about how you can instantiate isogeny-based versions of exotic signatures. So let's jump in. So we'll start with the question of what is a signature scheme, and a signature scheme is a scheme that allows you to achieve the following goal. So there's a person, Alice, and what she wants to do is publish a message in such a way that anybody who sees the message and some additional information that she provides can verify that the message really was published by Alice. And so there are many situations in which this might be useful. So for instance, digital contract signing. So Alice might publish a message and a signature that says, okay, I agree to the terms of a certain contract with Bob. And when Bob sees this message and signature, he believes that Alice has agreed to the terms of the contract as specified. And also importantly, Bob can convince others that Alice has agreed to these contract terms because somehow Alice is the only one who could have produced the signature. And this is important for things like dispute resolution. Another application where digital signatures are used are in software updates. So Microsoft may write a package and push it as a Windows update. And anybody who sees this package along with the additional information of the signature will trust that the update is legitimate. And what I mean by legitimate is that it was really published by Microsoft. They're also going to trust that it hasn't been corrupted by malware. So the message really is what Microsoft intended to push out. And then something else that another application would be transaction authorization. So Alice will send a message to her bank that says, hey, send $10 to Bob. And the bank sees this message and the signature and trusts that Alice really does want to send this money to Bob. And they also trust that, this message hasn't been modified. So it really was meant to say $10, not, $1. And Bob didn't modify it to get more money out of Alice. So these are the things that a signature scheme can accomplish. So let me just talk about what a signature scheme looks like abstractly. So in the abstract setting, a signature scheme is just a triple pi of algorithms called keygen, sign, and verify. The algorithms are denoted in this way because it should be indicative of what they're accomplishing. So first of all, keygen takes in a security level, lambda, which is somehow supposed to be how difficult it is to forge signatures. So it takes in some integer that tells you how strong your signature scheme needs to be, and it outputs a pair SK-PK. Here, SK is the secret signing key, and PK is the public verification key, which are used for signing and verification of signatures. So sign is an algorithm which takes in a signing key and a message, and it outputs a signature, sigma, on that message. And then verify, the third algorithm, it's an algorithm that takes in a public key, a verification key, a message, and a signature, and it outputs a bit B that's either of course 0 or 1. And now what this bit is meant to mean is that B will be 1 if the signature is valid and 0 if the signature is invalid. So let me talk about signature scheme correctness, and then shortly I'll talk about security. So this abstract definition says nothing about security or correctness. It just says there are 3 algorithms, and they somehow have to output things that look the right way. But it doesn't tell you anything about what it means to be secure or correct. It's just a structural thing. We say that a scheme is perfectly correct if, for all messages M, if we generate a secret key and public key using the keygen algorithm, and then we sign the message using that corresponding secret key, then the probability that the verify algorithm is going to output 1 if you give it the corresponding verification key, message, and signature, that has to be 1. So more intuitively, what this says is that a scheme is perfectly correct if whenever you generate a signature correctly, the verification algorithm will always tell you that that signature is valid. And this is intuitively exactly what you want. You want the scheme to work the way that it's intended to, that somebody who produces the signature will be able to, others who see that signature will then say, ah, yes, this really was generated by the person who claims to be generating it. Security, maybe unfortunately, but certainly in any case it is, it's much more complicated than just correctness. And the usual way that we approach it is through a game-based approach. So what I mean by this is that we think sort of abstractly of 2 players, one called the challenger, who holds the secret key, and the other called the adversary, who wants to break the scheme. And we think of these 2 players as playing a game. And then without telling you yet what the game is, we say that the scheme is secure if the adversary isn't able to win the game, except with very low probability. So then in order to really get a security definition for signatures, we need to define exactly how this game works. And sort of broadly, you can divide up the aspects of how this game works into 3 components. The first is the adversary's computational capabilities. The second is the adversary's interactive capabilities. And what I mean by interactive capabilities is, I mean, how does the adversary interact with the signature scheme or with the challenger who holds the public and private keys? That's what we need to define. And then third, of course, is the adversary's goal. I mean, they're playing a game, both players have a goal. So what is the adversary attempting to do in order to win this game? That's another thing we need to define. So there are lots and lots of options for all 3 of these, but for now, I'll just tell you about a few of the most prevalent ones and the ones that are important sort of in context. So let's start talking about computational capabilities, because I think this is sort of the easiest and most obvious thing you would need to define. So for signature schemes, I mean, if you look at cryptography more broadly than just signature schemes, there are lots and lots of options. You can talk about, computationally unbounded adversaries and statistical security, but for public key crypto, like of which signatures are an example, you really just sort of have two options. One is classical polynomial time. And what I mean by this is that the adversary can run any algorithm they want as long as it runs in time that's polynomial in lambda on a classical Turing machine, or maybe more simply a classical computer. And sort of the other thing you might think about is quantum polynomial time adversaries. Now, quantum polynomial time adversaries, they're able to run algorithms that run in polynomial time, but now they're running on a quantum computer rather than a classical computer. And maybe you're not, if you're not familiar with the difference between classical and quantum computing, it's not super important for the purposes of this talk. But the important thing, at least for us, is that if you're worried about quantum adversaries, you need to develop post-quantum primitives. And what I mean by post-quantum primitives is those protocols whose underlying computational problems are difficult for quantum computers to solve. And we'll see, I'm surely but we'll see later in this talk an example of a problem on which you can base a signature scheme that seems to be secure for classical adversaries, but is demonstrably insecure for quantum adversaries. And so there really is a necessity to develop post-quantum primitives. Okay, so that's computational capabilities. Now we'll take a second to look at goals. There are many different kinds of goals. And if we think about them in descending order of difficulty, so the absolute hardest one is a total break. And what I mean by a total break is that the adversary, they are allowed to run their polynomial time computations, and they're allowed to interact somehow with the challenger in ways that I'll explain in a couple of slides. And then there's somehow from those interactions and that computation recover the secret key. And of course, you can see why this would be disastrous, right? As soon as the adversary recovers the secret key, they've broken the scheme completely, because they can sign arbitrary messages and break the required security properties of the scheme. Next is what's called universal forgery. So at the end of the day, maybe the adversary can't recover the secret key because that's too difficult. But if they can still produce signatures on arbitrary messages, well, that's basically just as good as having recovered the secret key. So we would consider this a very strong attack as well, being able to sign arbitrary messages at the end of your interaction. Next is something a little bit weaker, selective forgery. So instead of, at the end of the day, being able to forge signatures on arbitrary messages, the adversary now is looking to be able to sign a message that they've chosen sort of in advance of the protocol. So they say, okay, I choose my message, m equals 10. And then I'm going to interact with you, and I'm going to perform some computations. And at the end of the day, I'm somehow going to come up with a valid signature on that message, m equals 10. And then weaker still is existential forgery, which basically the only difference between existential and selective forgery is that in an existential forgery kind of attack, the adversary is just looking to output a valid signature on a message that it doesn't get a signature for from the adversary, from the challenger during their interactions. And we'll talk about that on a later slide, exactly how that works. But the point is they need to produce a new signature on a new message, but they don't need to choose that message before they start the game, basically. And then even weaker still, and this is sort of the weakest one we would ever care about, is strong existential forgery, which looks a lot like existential forgery, except now the adversary doesn't need to produce a signature on a new message, but rather a new message and signature pair. And maybe it's not obvious why these two things are different, but the point is, in a strong existential forgery, it's possible that for the pair m and sigma that the adversary outputs at the end, they've already seen many signatures on the message m, but they just need to produce a signature that's valid for the message m that they haven't seen before. So that's the difference. And I mean, this sort of only makes sense in the context of randomized signing algorithms, because of course, if the signing algorithm is deterministic, there's only ever one signature for a message. So if you've seen one signature, that's the only one you could ever see. So strong existential forgery sort of is equivalent to existential forgery in that sense. And of course, so I say the word new several times here. So what I mean by new is that the challenger hasn't previously given it to the adversary, because obviously that would be a trivial way to break the scheme. That wouldn't really count as a break for obvious reasons. And finally, we're going to talk briefly about adversarial interactive capabilities. So in increasing order of strength now, so the weakest possible kind of adversarial interactive capability is what's called a key-only attack or a no-message attack, which is abbreviated NMA. And so what happens in an NMA attack is that the adversary is given the public key, which remember is used for verification. Is used for verification of signatures. And then after that, they don't interact with the challenger at all. And so in particular, they don't get any signatures. So all they see is the public key, and they need to somehow be able to, achieve some goal related to breaking the security of the scheme at the end of the day. This is a very weak attack. And in practice, this is not the kind of attack that we consider in theory or in practice because it's just not reasonable. It's too weak. So a more reasonable thing is what's called a random message attack, which is abbreviated RMA. And in this setting, there is actually some interaction between the adversary and the challenger. So the adversary gets the verification key. They always get the verification key. This is assumed to be public knowledge. But then in a random message attack, the adversary is also allowed to ask the challenger for signatures. And the way they're allowed to ask for signatures is to just say, hey, challenger, choose a message and send me a signature. And what the challenger does is they choose a random message, compute the corresponding signature, and return the pair m comma sigma to the adversary. Stronger still is a chosen message attack, which is abbreviated CMA. And in a chosen message attack, the adversary is allowed to ask the challenger for signatures on messages that it chooses now. So instead of saying, hey, challenger, please send me a random, please send me a random message and signature. Instead, I'm going to the adversary will send the challenger a message and receive the corresponding signature. And if you just excuse me for a moment, I just got to see a question in the chat that I'll try to quickly address. So the question is, can we think that all the problems which takes exponential time on a classical computer can be solved in polynomial time by a quantum computer? And if not, what exactly is the relation? So that's actually a very deep question that I can't answer very fully, but short answer is no. There are problems which we know, there are problems which we don't know how to solve in polynomial time on a quantum computer, even though they're what am I trying to say? Let me phrase this better. There are problems which we don't know how to solve easily on a quantum computer that are exponential time on a classical computer. So it's not saying that every problem that's hard for a classical computer we can make easy on a quantum computer. And that's actually sort of the fundamental thing of post-quantum cryptography. And we'll get to that when we talk about isogeny-based cryptography. But anyway, just to refresh the slide, there's key-only attacks, random message attacks, and chosen message attacks. These are the primary interactive capabilities we consider for the adversary. So interestingly, if you read some of the more niche literature on the subject, sometimes we even allow quantum interactions, which is kind of interesting. So a quantum chosen message attack, in this setting, the adversary is allowed to ask the challenger for signatures, not just on messages, but actually on superpositions of messages. So if you're not familiar with quantum computing, this part probably won't make a lot of sense, and it's not super important. But just for the sake of for those of us who are familiar, what this looks like is the adversary is going to provide a quantum state, which is this quantum superposition over all messages m with corresponding amplitudes alpha sub m. And then the challenger, what they're going to do is they're just sort of going to naively sign each message in the superposition and provide this as a quantum response. So you can see how this is stronger than a quantum chosen message attack because if you want, or sorry, is stronger than an ordinary chosen message attack because the adversary can simply send pure quantum states which are not in superposition, and this will sort of emulate an ordinary chosen message attack. Anyway. The thing with this model is that while it is sort of interesting theoretically, a real world signer would never actually sign a quantum superposition of messages using a classical scheme. So generally in the papers that I've looked at and the papers that I've read, you would never actually, you don't really use this this definition much, but it has been in some papers and it is sort of interesting. And similarly, so when we're talking about newness, remember when I talked about forgeries, existential forgeries, strong existential forgeries, we needed a notion of new messages because if you're signing an old message, I mean, that signature could have been provided to you by the challenger. So we need to sort of adapt our definition of newness when we're considering quantum queries. And now why is that? Because, well, if the adversary requests a signature on a superposition of messages where now somehow they can, this superposition can be over all valid messages. And And so somehow, maybe intuitively, they're receiving a signature on every single message that's possible. And you would say, well, okay, so they've received a signature on every single message. So how does this, how is any message even new at this point? And the sort of non-answer that I'm going to give is that even though somehow this state encodes the information of a signature on every message, you can only really extract, hopefully, one signature out of this. So in some sense, you're getting something that has hidden inside of it. This quantum state has hidden inside of it all of these signatures. But at the end of the day, in a secure scheme, at least, you can only extract one signature from this quantum state. And then with this sort of this idea in mind, the way we redefine the existential forgery is that instead of saying, okay, I need to get a forged signature on a new message, it just says, okay, if you've made n signing queries, we're assuming you can extract n signatures. So n is a trivial number of signatures for you to provide, but if you can provide just one more, then you win the game. So that's the difference between newness in the classical and quantum interactive settings. But anyway, you have all these notions of security, and you can just mix and match the pieces to make complete security definitions in basically any way you want. And usually, when we're talking security, I mean, signature schemes have existed for a long time, and we've come to have high standards for what it means for a signature scheme to be secure. And what that really means is that we want the strongest security guarantee that's possible. And so, in particular, that means the most computationally powerful adversary, the most interactive capabilities, and the easiest goal, because if we can guarantee that the adversary cannot do the easiest thing, even when they're as powerful as possible, then we have a high level of certainty about how secure our scheme is. So for this reason, in the literature, generally we go with strong existential unforgeability, and we allow the adversary to perform a chosen message attack. And in some settings, like I said, we even allow a quantum chosen message attack, but that seems to be a little less common than just an ordinary chosen message attack. Okay. Yeah, like I said, some works consider quantum chosen message attack, but it's hardly ubiquitous. It's not something you need to worry. I think maybe later down the line, it's something to be interested in, but just concretely for now, people are mostly concerned with chosen message attack. Okay, so we still, what I said is that, you have this game that you define in terms of these three parts, these computational capabilities, these interactive capabilities, and these the goal, of course. But then you say, okay, the scheme is secure if the game is hard to win with high probability. So I still need to qualify that last part. So what do I mean by hard to win? Or how do I quantify or qualify what it means to be hard to win? Unfortunately, it's quite difficult to make quote unquote absolute statements about the security of signature schemes, because frankly, because complexity theory just doesn't have all the answers that we need yet. It's possible that later complexity theory will be able to make more absolute statements, but for now it can't. So in particular, what I mean is that it's quite difficult to make meaningful statements of the form, breaking this signature scheme requires at least T operations, where like T is big enough that we are sort of we accept that something is cryptographically secure. However, what we can do is make statements that are weaker than this. We can say, okay, I have this signature scheme, and somehow underlying it is this difficult computational problem. And what I mean by underlying is that if you can break the signature scheme, so if you can, produce your existential forgery, or recover your secret key, depending on the game that you're playing, then you can solve the corresponding computational problem. And this statement is useful on its own. It relates the computational problem, the hardness of that, to the security of the signature scheme. But then we often make these statements sort of conversely. So if you take the converse of this statement, it says, if the computational problem is hard, then the signature scheme is secure. And these are basically the kinds of theorems that we make in public key cryptography. We say, okay, I've got this computational problem. If that's hard to solve, then the signature scheme is secure. And then later on in your paper, you'll say, I assume that this computational problem is hard, and therefore, by my theorem, the signature scheme is secure. So that's the fundamentals of signature schemes. Let me just quickly go over an example of a signature scheme that you would see, in a typical cryptography class probably. This is called full domain hash RSA signatures. So the way it works, the most complicated part is the key generation. Thankfully, the other parts are even simpler. So the secret key is a pair, or is 4 numbers. It's P, Q, N, and D, while the public key is N and E. That's the same N there in the public key and the secret key. And here, P and Q are distinct primes. N is P times Q, and E times D is congruent to 1 modulo phi of N. Here, phi is Euler's Teuton function. So with all of this in mind, if you want to sign, what the signer does is they take their message M, they take the hash of it under some sufficiently cryptographically strong hash. I'm not worried about hash functions in this talk, so just pretend it's a very nice hash. And they raise that to the power of D, modulo N. And then to verify, the verifier simply checks that the signature to the power of E is congruent to the hash of M modulo N. And if that's true, then they say that the signature is valid, and otherwise they say that the signature is invalid. So why does this make sense? Well, I mean, we can look at correctness first. So if sigma is h of m to the power of d modulo n, then if we raise that to the power of e, then of course we get h of m to the power of e times d. This is just how exponents work. And then of course we know that the order of the group Zn star is phi of n. So we can reduce this exponent modulo phi of n, and by construction, e times d is 1 modulo phi of n. So this just gives us h of m. And so this is the exact thing that we were checking on the previous slide. So this verification procedure works. The signatures really do have the correctness property that they want. As it turns out, full domain hash RSA signatures are existentially unforgeable against chosen message attack, even strongly. I mean, the scheme is deterministic. So of course it's going to be, if it's existentially unforgeable, it's strongly existentially unforgeable. And it's going to be that way if against classical adversaries. Note that I specifically say classical adversaries. If the hash function is one way and the RSA problem is hard. Now, what's the RSA problem? It's something you've likely seen in a textbook or something even. It's just if you give me D, which is co-prime to N, and you give me M to the power of D, you want to recover M. So this scheme, like I said, secure if you make some very reasonable assumptions. But if you now move into the quantum era, the RSA problem is known to not be hard for quantum computers, which is classically, we don't know whether it's easy or hard. Like we have some idea of like, oh, okay, we can solve it in like sub-exponential time maybe, but not polynomial time, but we know it doesn't take exponential time, but we know that we think it's hard enough. But in the quantum era, we know for a quantum computer, this problem is actually not hard. And the reason is as follows. So first of all, solving the RSA problem is easier than factoring. And the reason is that if you can factor n, then you can compute the Teuton function phi of n, and then you can use that to compute the secret signing key from the verification key. So we've reduced the problem to factoring. Now factoring we also don't really know how to do classically, and that's where quantum computing comes in. As it turns out, factoring is easier than order finding. And what I mean by that is if you can find the order of a group element in a group of a certain form, then you can factor. And this is where the quantum computer comes in, because this circuit here, which it's not important what the details of the circuit are, I just think it's a nice picture. This quite small quantum circuit solves the order finding problem efficiently. So what this says is that quantumly we can solve order finding. Order finding lets us factor, and factoring lets us solve the RSA problem. So now we know that full domain hash RSA is not secure in the quantum era. And that's why we need to talk about quantum safe alternatives. So yes, that's all I wanted to say about signature schemes, sort of the fundamentals of them. And now we're going to move in to talk about exotic signatures. But before I can talk about exotic signatures, I need to talk about the motivation for exotic signatures. And that motivation is thinking about what security guarantees are actually provided by ordinary signatures. So signature schemes, as I've described them in the previous 15 slides, they provide 3 main guarantees. The first is what I call data origin authentication. So what I mean by this is that verifiers, somebody who verifies a signature and sees that the signature is valid, is convinced that the person who claims to have signed the message really did. Then we have authenticity, which says that a verifier is convinced that the message contents have not been altered. And that's because if you alter a message, you need to produce a new signature, but only the person who knows the secret key, the signing key, can produce these signatures. And then 3 is non-repudiation, which is that a verifier can convince a third party of which person produced a signature on a given message. And the way you do that is you say, oh, look, this is a valid signature on this message. The only person who knows the signing key is Alice. So Alice must have signed this message herself. So these are the 3 main properties, security properties provided by ordinary signature schemes, as we've discussed in the previous slides. However, there are many applications where these guarantees are not sufficient. And that, of course, because I mean, these signature schemes were designed with certain goals in mind. And if you come up with new goals, then of course the scheme is not going to be sufficient anymore. You're going to need a new scheme. Exotic signatures, as I call them, well, me and my colleagues, and hopefully other people will be calling them, are variants of signatures which provide different or additional guarantees beyond, or maybe in opposition to these. So a natural question is, what kinds of exotic signatures are there? And there's sort of as many kinds as you want. The thing is, if you come up with a use case that something that looks like a signature can satisfy, and you come up with a protocol that works, then that's an exotic signature. But of course, they've been sort of classified into many different kinds. In this talk, I'm only going to talk about the ones for which there are isogeny-based exotic signatures. Only those types of exotic signatures for which there are isogeny-based instantiations. And so in particular, there are 3 that, well, there may be 4. One of them is in my mind, it's not clear to me whether it's secure or not, but there's certainly 3. So those are the 3 I'm going to talk about today. We've got threshold signatures, ring signatures, and linkable ring signatures, which are really just a variant of ring signatures. So we'll consider them the same for now. And adapter signatures. And I've listed them sort of, at least in my estimation, of how difficult they are to understand. So threshold signatures, I think, are fairly easy. Ring signatures are a little bit more complicated. And then adapter signatures, they took me a while to wrap my head around, but I hope to be able to get the ideas across to you today. So in these next few slides, I'm going to talk about the features and applications of these things. And in particular, for each of them, I'm going to talk about a few applications and hopefully at least one blockchain related application for each. And then later, once I've refreshed everyone's memory about how isogeny-based cryptography works, we'll talk about the isogeny-based instantiations of these things. So let's do that. What is a threshold signature? So a threshold signature, the intuitive explanation is that they allow signing authority to be split among members of n people, members of a group of n people in the following way. So if k or more of these people cooperate, then they can produce a signature. But if k minus 1 or fewer of these people cooperate, they can't produce signatures at all. So somehow this, the k people is the threshold for being able to produce signatures on messages. So the application, I would say, is quite straightforward. Instead of one person having authority over an account, you can give authority over an account which contains some currency to a group of people, and a sufficient number of people must cooperate in order to do anything with that account, to access the funds in the account. This is like a joint bank account. Which ordinarily the way a joint bank account works is that you need to collect people physically together and they all sign a piece of paper or something. But using threshold signatures, you can do sort of an analogous thing where enough people need to get together to digitally sign something. And then so the way I phrase this, it says there's a group of size n and you need k people to produce a signature, but you can actually generalize this to what are called arbitrary access structures. And what I mean by this is that if you take a collection gamma of subsets of the participants, 1 up to n, and as long as this collection is monotone, meaning that if you take any set in there, and then let's call that set A, and then you take a set A prime that contains A, then A prime is also in gamma. And this intuitively makes sense, or it will be intuitive why this makes sense. But the point is that if you have this monotone collection gamma of subsets, then if A is in the subset, they're able to produce signatures. But if B is not in the subset, then that collection cannot produce signatures. But for the purposes of this talk, I won't be talking about arbitrary access structures. It's sort of a generic transformation that's been around for some years. So it's not really the interesting part of threshold signatures. So like I said, I think these are the simplest ones to understand. Next, we're going to move into talking about ring signatures. So a ring signature scheme is, in some senses, if you're familiar with group signatures, it's sort of like, at least if you're far enough away and maybe you're squinting, they sort of look similar, but they're actually, yes? Oh,
No, Professor, you can go ahead.
oh, sorry,
can,
sorry.
Yeah, you can go on.
Okay, I'm back. Okay, sorry about that. So a ring signature scheme, it allows a signer to sign a message on behalf of an ad hoc collection of users called a ring. And what I mean by ad hoc is that the signer can arbitrarily, at the time of signing, pick a bunch of people and say, I'm signing on behalf of this ring, which is all of these people plus me. And this group of people is called a ring. So let me write this down more formally. So let R be a collection of public keys, PK1 up to PKN, and they're owned by parties P1 up to Pn. And let's let SKJ be the secret key corresponding to public key PKJ. So party PJ can sign what I call on behalf of the ring R. So they can produce a signature. Now the signing algorithm takes in the secret key of the jth participant and the public keys of all the ring members and the message, of course, and produces a signature. And now a verifier can verify not with respect to the secret key, with respect to the public key of the jth user, but with respect to the entire ring. So the verifier provides all the public keys, the message, and the signature, and they get this bit B, which remember is 1 if the signature is valid and 0 if the signature is invalid. And what they learn is the verification algorithm will output B equals 1 if and only if sigma was produced by somebody in the ring. However, the signer's identity is not revealed. All you know is, if the ring has 100 people, then you have 100 candidates for who could have produced the signature, but you don't know who it is. So what are some applications of ring signatures? The sort of natural way you would want to apply them is in situations where there's some sort of compromise between proof of authority, which you can think of as being given by an ordinary signature scheme, but also you want some level of privacy. And so let me just give a couple of examples of contexts where this might be useful. And I believe, if memory serves, authoritative leaking is the original setting in which people were considering the use of ring signatures. So what is authoritative leaking? It's best explained through an example, of course, like many things. So suppose there's a company and there's a manager working at this company who has evidence that a high-ranking board member or whatever at the company has been involved in illegal activity. So a ring signature will allow the manager to release information in a way this information to the police or the public or something in such a way that he doesn't open himself up to reprisal from the board member, but still people believe that this is coming from someone with insider knowledge. And the way they do that is the manager releases the information and signs on behalf of the ring of all managers at the company. So any verifier who sees the signature says, oh, wow, this evidence definitely comes from a manager at the company. So that's somebody relatively authoritative. This is good information that I can believe. But nobody can figure out which manager released the information. All you know is that it's some manager, and this prevents retaliation. Another situation, less, a different situation, we'll say, is private transactions in a joint account. So you can consider a group of people who all have authority over an account, and you want that any user can authorize a transaction for the account, but you don't want to be able to trace it back to which particular user authorized the transaction. And a ring signature is exactly accomplishes this, right? Because what a ring signature does is you say, okay, I'm signing on behalf of all the users of the account, but I'm not going to tell you which user I am. But you can still verify that it was some valid owner of the account. So these are two situations where ring signatures might be useful. Let me just talk briefly about the security of ring signatures, because it does have some different properties from an ordinary signature scheme. And in particular, in addition to unforgeability, you want ring signatures to guarantee anonymity. And what that means is that a verifier and even other ring members can't figure out the identity of the signer. And this is a very strong definition, in fact, stronger maybe than it even seems on its face. So in particular, the anonymity must hold even in the face of very strong properties like insider collusion, which means that if other ring members collaborate, they still can't determine who produced a given signature. And maybe even more surprising is against full key exposure. And what this means is that even if a signer's secret key is later revealed, ring signatures that they produced before this exposure must remain anonymous. So learning somebody's secret key mustn't de-anonymize their ring signatures. So it's quite a strong definition. Now, in the context of cryptocurrency and blockchain, I haven't seen ring signatures, plain ring signatures used. What I have seen, however, are linkable ring signatures. And so these are a variant of ring signatures in which you don't provide just a signature, but you also provide additional auxiliary information called a tag. And what the tag does is it lets you tell whether two signatures were produced by the same user. So as with ordinary ring signatures, linkable ring signatures need to provide anonymity to the greatest possible extent. Now, it's just a matter of what is meant by the greatest possible extent. In the setting of ring signatures, it was obvious. You say, okay, I signed on behalf of this ring, and you can't tell which ring member made the signature. All you know is that it was one ring member. For linkable ring signatures, you have to weaken this a little bit because, well, for the following reason. So if I give you n signatures with tags, so sigma 1 T1 up to sigma n Tn, and these are signed on behalf of different rings, R1 up to Rn, and suppose these are all linked, which means that they're produced by the same user. Well, the first signature is produced by somebody in R1, and we don't know who. And the second signature is produced by somebody in R2, and we don't know who, and so on. But they're all produced by the same person. So what this means is that the person who produced all of these signatures is in the intersection of all these rings. And so in particular, if the intersection of all these rings only contains one person, then you can identify that person who made all of these signatures, and that's totally unavoidable in the context of linkable ring signatures. So all we need to guarantee is that if you take the intersection of all these rings, you can't determine which user from that intersection produced all the signatures. That's what we need to guarantee in a linkable ring signature. Now let's talk about applications. So linkable ring signatures are usually applied in situations where, as before, you require anonymity and proof of authority, but then you also want to guarantee that users can participate only once in this process. So a very natural application is what I call anonymous public electronic voting. So what do I mean by this? So suppose we wish to hold a vote publicly. And what I mean by this is that, all the votes are published on a board somewhere. So you can say, okay, one vote for party 1, one vote for party 2, another vote for party 1, and so on. But you don't want these votes to be associated to the people who cast them, of course. That's usually not how it goes. But at the same time, sort of contrary to that, you want to make sure that only people who are qualified should be able to vote. And so maybe these are people who are old enough and they live in a certain area, and so they're compatible with this election. And then finally, the last thing you need is that nobody should be able to vote twice. So ring signatures, linkable ring signatures, allow you to prove this. And the way that it works is that everybody who's participating in this election will submit their vote along with a signature signed on behalf of all valid voters and with a tag, which is of course required for a linkable ring signature. Then all you need to do is check that all the signatures are valid. So that way you know that every vote corresponds to a person who is eligible to vote. But then also you check that no two tags are the same. And if all the tags are different, the signatures were submitted by different people, and thus the votes are all from unique individuals, and nobody has voted twice. So this is one setting in which a very natural setting in which you might use a linkable ring signature to achieve public voting. Now, in cryptocurrency, linkable ring signatures are used to simultaneously provide three important properties. The first is that they provide security. The second is that they provide anonymity. And the linkable part is where you use them to prevent double spending. And this is a little bit complicated, so I'll just give a brief overview of how it works. So very briefly, if you want to perform a transaction, the user who owns a certain coin is going to use the secret key which is associated to that coin. It's not like the user has a secret key for their account, although they also have that, but somehow they have the secret key for the coin or coins that they want to spend. Now, the user is going to sign on behalf of a ring that contains the corresponding public key of their coin, but then public keys from a bunch of other transactions, a bunch of other coins that aren't actually involved in the transaction. So this will give a certain level of anonymity because outsiders can't tell which coins are being spent, which is kind of interesting. Now, any future signature that links to a prior signature is invalid because it corresponds to, quote unquote, spending the same coin twice. And the important thing to remember when you're doing this is that once the coin is spent, it gets a new secret key. and the new owner has the new secret key. So if you see the same tag twice, say, then that corresponds to a coin being spent twice, and that will be an invalid transaction. So this is how linkable ring signatures can be used for cryptocurrency. And so for the final type of exotic signature we're going to talk about, those are our adapter signatures, and we'll get to those now. So I think the intuition is less there for adapter signatures, but the application is pretty interesting. So maybe these next couple of slides will be a bit of a slog, but the application is pretty cool. So adapter signatures, they start with an ordinary signature scheme and then add additional phases called pre-signing and extraction. And these phases are dependent on what I call a hard relation. And I'll define all of these things. So a hard relation is a set R, which is a set of pairs big Y comma small y. And now the big Y's are called statements and the little y's are called witnesses. And now this set of pairs has the following three properties. The first is that if you want to generate an element of the set, that has to be easy. The second is that if I give you an element and I say, hey, this thing's in the set, it needs to be easy to determine whether or not that's true. And then the third thing is, if I just give you a statement, it needs to be difficult to find a witness corresponding to that statement in the relation. And so maybe this definition is a bit abstract, but sort of the prototypical example is the following. So if you let G be a cyclic group generated by little g of order n, then you can let the relation R be the set of pairs G to the Y comma Y. So let's just look at this. Why does it satisfy the three properties? Well, if you want to generate something in there, you choose little y, and then you set big Y equal to G to the little y. So that's easy. It should be easy to determine whether big Y comma little y is an R. That, of course, is easy. If I give you G to the Y and Y, I mean, you can verify this equation. You take little g, put it to the power of little y, and check if it gets what I claimed it was. And then thirdly, why is it difficult? Well, the discrete logarithm problem, at least for classical computers, is believed to be difficult. So if I just give you big Y, which is equal to G to the little y, it's not easy to come up with the corresponding witness. So this is a prototypical example of a hard relation. It's not one we use in post-quantum cryptography, of course, because discrete logarithms are also easy for quantum computers. So let me talk a little bit more about the structure of an adapter signature. So it has, it has algorithms that it inherits from the underlying signature scheme pi, but it also gets four more algorithms called pre-sign, pre-verify, adapt, and extract. And they work as follows. So pre-signing is a lot like signing. It takes in a secret key and a message, but it also needs to take in a statement from the hard relation, and it produces what's called a pre-signature sigma hat. And this pre-signature depends on the message and, like I said, the statement from the hard relation. Now, pre-verifying works a lot like signature verification, except now it also depends on the statement of the hard relation. So it takes in a public verification key, a statement from the hard relation, a message, and a pre-signature, and it tells you whether or not sigma hat is a valid pre-signature on that message with respect to the hard statement, or the statement of the hard relation. Now, adapt takes in a pre-signature and it converts it into a signature from the underlying signature scheme, but it needs the witness for the corresponding statement in the hard relation in order to do this adaptation. So somehow, people who are pre-signing are going to be choosing statements and witnesses from the hard relation, and then later will be adapting things using the witnesses which they've kept secret. And then sort of interestingly, extract, it takes a signature and a pre-signature, both of which correspond to the same statement and the same message, and it's going to produce a witness for the statement. And this is something that the signing party will not be using. It's the verifier who's going to be using this for something in the context of cryptocurrency. But these are the additional algorithms. So basically, you can think of pre-sign and pre-verify as being totally analogous to sign and verify from an ordinary signature scheme, except that it's done with respect to a statement from a hard relation. Adapting is how you turn pre-signatures into signatures, and extracting is how you recover witnesses from statements given signatures and pre-signatures. And it'll be more clear later why you need extraction in particular. So I'm not going to go into the details of adapter signature correctness because it's quite tedious. But as with the other protocols, we call an adapter signature scheme correct if, quote unquote, everything works the way it should. And what do I mean by that? Well, if somebody produces a pre-signature using the corresponding algorithms, this must pass verification. If you adapt a valid pre-signature, it must always produce a valid signature. And if you have a signature and pre-signature corresponding to the same statement and message, you must always get a valid witness from the extraction algorithm. So everything just works the way that I described it on the previous slide. That's what it means for the adaptive signature to be correct. As for security, well, the first thing we need is for the underlying signature scheme to be secure. And then we need to add, of course, additional properties because there's more algorithms going on. So the first is what's called adaptive unforgeability. And what this says is that it must be difficult to forge a signature in the underlying signature scheme, even if you have seen a pre-signature with respect to some statement. So somehow you're getting more information than you would normally have, but it still needs to be difficult to produce a signature from a pre-signature. Next, we have adaptability. And so it must be difficult for a cheating signer now. So this is interesting. So usually when we're talking about security of signatures, it's the verifier who's trying to cheat and forge a signature. But this is actually a game that the signer is playing. So it must be difficult for the signer to construct a pre-signature which will adapt into an invalid signature, even given the witness. And then extractability says it must be difficult. This is again a game that the signer is playing. It must be difficult to construct a pair sigma, which is a signature, and sigma hat, which is a pre-signature, which doesn't yield a valid witness when you apply the extraction algorithm. So, like I said, this is quite different to how other signature scheme security aspects are modeled, because adaptability and extractability here, these properties are to protect the verifiers from cheating signers instead of protecting signers from cheating verifiers. And I'll explain on the maybe on the next slide or the next couple of slides why this is important. So yeah, on this slide here. So let me tell you about why you would use adapter signatures. So in the context of cryptocurrency, they're used to execute what are called atomic swaps. So what is an atomic swap? So intuitively, what an atomic swap accomplishes is it allows two mutually untrusting parties. So Alice and Bob, they want to exchange some assets, but they don't trust each other. So I mean, if they trusted each other, the solution is clear. Alice sends her thing to Bob, and Bob sends her thing to Alice, his thing to Alice, and they do this sort of asynchronously or whatever, because they trust that the other party is going to cooperate. But if they don't trust each other, then sort of game theoretically, nobody wants to act first by sending their asset. So one way you could solve this is by using a trusted third party, like an escrow service. And the way that would work is, Alice sends her asset to Charlie, Bob sends his asset to Charlie, and then Charlie distributes the assets to Bob and Alice respectively. But adapter signatures let you execute atomic swaps without the need for this escrow service, which is quite interesting. And here's how it works. So the first thing that Alice is going to do is choose a statement witness pair from the hard relation, and she's going to pre-sign what I call authorization to send her assets. So this message M that I put in the pre-sign algorithm is a message that says, I, Alice, agree to send Bob, 10 Bitcoin or something like that. And she pre-signs it, and she provides this pre-signature to Bob. Bob takes the pre-signature and verifies that it really is valid for the statement and the public key and the message, all from Alice. So he makes sure, he said, yep, this really is a pre-signature that says you're going to send me 10 Bitcoin. Then what Bob does is he uses the same statement from Alice to pre-sign authorization for him to send his asset to Alice. So maybe his message M prime says something like, I Bob declare that I will send 100 Ethereum to Alice, something like that. And he produces this pre-signature sigma prime. Now, what Alice does with this pre-signature is that she adapts it into a signature on Bob's message, and she can do this because she knows the witness, little y, to the statement in the hard relation. And once she has the signature, she can send it off to the blockchain, and it says, oh, Bob has authorized this transaction, so I will send the 100 Ethereum over to Alice from Bob's account. Now, seemingly Alice has won, right? She has the asset from Bob. How is Bob going to guarantee that she keeps up her end of the bargain, right? Bob wants to get his assets out of Alice. And the way he does this is using the extract algorithm. So he sees well, of course he knows sigma hat prime. This is the pre-signature that he generated. And then he can look at the blockchain where Alice used his signature to obtain his asset, his Ethereum in my example. And then he can use the extract algorithm along with the statement, and of course these two, the signature and pre-signature that I just talked about, to extract the witness to the statement. And then once you know the witness, of course, Bob can use the adapt algorithm now on Alice's pre-signature to construct what would be Alice's signature. And then he can publish this, and in so doing, this authorizes the transaction, and Alice will, Alice's 10 Bitcoin will be sent to Bob. If you look at adapter signatures sort of abstractly, at least when I looked at them first, it wasn't clear at all how you would use them for anything reasonable. But this idea of an atomic swap without escrow service is quite interesting, and this is the main application in the context of blockchain. Okay, so that's a lot of material about exotic signatures. And now I'm going to try and talk about how you instantiate them using isogeny-based cryptography. And of course, before I do that, I'm going to have to talk for a minute on what isogeny-based cryptography is. So at the highest level, isogeny-based cryptography refers to cryptographic schemes whose security is based on the hardness of finding isogenies between supersingular elliptic curves. And as I understand, my colleague, Dr. Yan Boti, spoke yesterday, and he introduced isogeny-based cryptography. So I will only very briefly review what is needed. Now, thankfully, isogeny-based cryptography, I said thankfully, so I'll say the good part first. Superficially, a lot of isogeny-based cryptography heavily resembles Diffie-Hellman, which is quite standard and relatively easy to understand. Now, unfortunately, the underlying mathematics is quite a lot more difficult than Diffie-Hellman, but I'm going to describe it at a fairly superficial level, which should be sufficient for understanding the protocols. But yesterday's talk would have introduced the mathematics at a more in-depth level. But anyway, I'll just briefly review what I need. So in particular, all I need is complex multiplication and this protocol C-side, which stands for commutative supersingular isogeny Diffie-Hellman. So I'll describe them here on this slide. So the first thing you want to do for C-side is you take these, a bunch of small primes, L1 up to Ln, these are distinct odd primes, and then you take P to be 4 times the product of those primes minus 1. And you want this P to be prime. Then what you do is you consider the set of all elliptic curves whose FP rational endomorphism ring is isomorphic to Z adjoint pi. Now here pi is, you can think of it as being the square root of minus P. So we have these elliptic curves, and if you think about their endomorphisms, which are FP rational, you want that ring to be isomorphic to Z adjoint the square root of minus P. Now, the ideal class group of Z adjoint the square root of minus P acts on this set of elliptic curves by complex multiplication. And now what is complex multiplication? Well, okay, so the ideal class group consists of, as the name suggests, ideal classes. And if I want to act an ideal class on an elliptic curve, I do the following. So I take an integral representative of the class, call it A, and this thing is a bunch of, it's an ideal in the FP rational endomorphism ring, so it's a bunch of isogenies. And so these are functions. And what I do is I take the intersection of the kernel of all of these functions. And that's going to give me a group. And as we know from Beilous formulas, if I give you a group, say it'll give you, in this setting, it'll give you a cyclic group. If I give you a cyclic group, that's the kernel of an isogeny. And what I mean by this slash is I take the image of the isogeny whose kernel is that group. So that's how the ideal class group acts. This is complex multiplication. Of real special interest to us in C-side are the ideals that look like this. They're, let's just say, I'll omit the subscripts in my speech because it's too messy, but so we've got L and L bar. So L is generated by multiplication by the number L and Frobenius minus 1, and L bar is generated by multiplication by L and Frobenius plus 1. And I'm not going to explain why, but the important thing is that their action is very easy to compute. And so the way that C-side works is that you generate a key by choosing exponents for a bunch of these ideals Li, and then you apply the ideal the corresponding number of times. This action is very easy to compute. Now, I don't know whether this was in the talk yesterday, so I'll explain it here. So in C-side 512, the way that which is the sort of lowest level, lowest security level of C-side that we really think about. The way that we compute the action of ideal classes is by writing them like this. We write them as L1 to the E1 times up to Ln to the En, and then what we do is we apply, Ln En times and L1 E1 times and so on for all of the ideals. And this is great for computation. It's reasonably efficient. However, it's important in signature schemes, well, in zero knowledge proofs, which will later become signature schemes, that we're able to sample from the class group uniformly. And in C-side 512, we're very fortunate to be able to do that, because it was quite a difficult computation, but we actually know that the ideal class group, this thing here, is generated by an ideal, which I'll just call G, an ideal class called G, which is of some order n, which we know explicitly. And we have this method where if I give you an exponent, I can convert G to the A into something that I can compute with. And so we're going to use this representation to sample uniformly in the group, and then we're going to convert to this convenient computational representation when we're computing. But for my purposes, I'm not talking about computational issues much in this talk, not beyond this slide even. So for us, we're going to be thinking about ideals as looking like this on the right here. Sorry, on the left here. Okay, so that's my one slide discussion of C-side. That's really all there is to it. So with this sort of background in mind, I'll explain now how you get a proof of knowledge and consequently a basic signature scheme out of this. So the key ingredient to realizing most C-side based exotic signatures is a proof of knowledge, a zero knowledge proof of knowledge. And in particular, what you prove is that, okay, so you're going to publish somewhere a base curve E0, an ideal class G, and a target curve EA, and you're going to prove to somebody that you know an exponent A such that EA is G to the power of A acting on E0. So this is what the proof of knowledge wants to accomplish. And you can think of this as being totally analogous to Diffie-Hellman-based proofs of knowledge, where you're going to publish G and G to the A, and you're going to prove to somebody that you know A without revealing it to them. So it's like knowledge of a discrete logarithm, basically. And the basic protocol is actually very reminiscent of the one that you would use in the Diffie-Hellman setting. So the way that you do it, the prover is the one who wants to prove that they know little a here. So what they do is they choose R, and they send out E sub R, which is G to the power of R times E0. Now the verifier is going to choose C, which is either 0 or 1, and it's called the challenge, and they send the challenge to the prover. Now, if C equals 0, the prover sees this and they say, okay, I'll reveal R. I'll prove to you that I was playing the game properly because I know the R that relates E0 to E sub R. And now otherwise, they're going to, if C equals 1, that is, they're going to reveal R minus A modulo N. Here, N is the order of the group. So what the verifier will check, well, if C is equal to 0, they'll check that the prover was playing the game properly. They'll say, okay, is G to the power of R times E0 equal to ER or not? And if it is, they say, great, we trust that the prover was playing properly. And then if C equals 1, they'll instead check that G to the power of R minus A, this is the thing that the prover sent over, and they'll, instead of applying it to E0, they'll apply it to EA. And because EA has a G to the power of A times E0, when you apply G to the power of R minus A, the A's will cancel, you'll get G to the R times E0, and that will give you ER. So either way, you get ER. So somebody who wants to cheat and pretend that they know A when they don't, they can win with probability 1/2 by just guessing what challenge they're going to receive from the verifier and acting accordingly. So what you do is you repeat this lambda times. Maybe lambda is 256. You say you repeat this 256 times. They're all independent trials, so the probability of a cheater winning 256 times in a row is quite low. And at that point, you would trust that the person you're talking to really knows little a. And importantly, the Fiat-Shamir transform takes this proof of knowledge, which is an interactive thing, and transforms it into a signature scheme. And I'm going to talk in the next slide on the Fiat-Shamir transform. So it's used to transform interactive zero knowledge proofs of identity, like on the previous slide, into signature schemes. The idea is quite ingenious, but also quite simple. So the idea is that now the prover is going to generate their own challenges. And normally that would be insecure, because if the prover knows the challenges in advance, they can play the game, quote unquote, wrong and win with probability 1. However, they need to produce the challenges in a special way. They take their message and then all their commitments, so they need to commit to these curves, and then they're going to use that as a random seed to generate the challenges. And the idea is that if the way these challenges are generated from the seed is sufficiently unpredictable, the prover, a cheating prover, can't game the system and cheat. So this removes the need from a challenger, which is great because it makes the scheme non-interactive. Now the signature is going to commit of the challenges, the commitments, and the responses, all of these things. This is what a verifier is going to need. And what the verifier does is the first thing they do is check that the responses are correct, which says, hey, he really did know the answer to all the instances of the zero knowledge proof. But then the verifier also recomputes the challenges using the messages and the commitments. And this ensures that the prover really did construct the challenges fairly, and thus it really must know the secret in order to produce the signature. So I won't dwell on this. The important thing is that there's a protocol that takes a zero knowledge proof of identity, or a proof of knowledge from like on the previous slide, and produces a signature scheme. And this is how all isogeny-based exotic signatures work. So there are three, well, I guess there are four, but I'm only going to talk about three isogeny-based exotic signatures that build upon this proof of knowledge. The first is a threshold signature from DeFeo and Meyer. The second is called calamari, and that's an isogeny ring signature. And the third is called IAS, and this stands for isogeny adaptive signatures. And these are, as the name suggests, adaptive signatures. So these protocols are quite complicated, and I've got 25 minutes left or something. I would never have had time to discuss them in detail. I will, however, discuss their sort of underlying basic protocol, and then just briefly say why this leads to the scheme that you want. Yeah, there you go. See, I already had this built into the slides. I knew how this was going to go. So let's talk about threshold signatures. So the DeFeo-Meyer scheme is based on polynomial interpolation. So what do I mean by this exactly? So let's let F be a map from ZQ to ZQ of degree k-1. And the key thing to know about these kinds of maps is that if you only know k-1 points, then any constant term is possible. So if say 1 point on a line, then yeah, that's no good. You can't tell what the constant term is. But if you know k points, then actually the constant term is completely determined by the points you're given, and it's just a formula. The exact value of the formula isn't important, but the idea is there is a formula that lets you recover the constant term. And you use this to split the knowledge of little a, which is sort of the quote unquote base of the logarithm in this proof of knowledge. So instead of talking about threshold signatures now, I'm going to talk about what I call a threshold proof of knowledge. So we want any k of n parties to be able to prove knowledge of this little a such that e sub a is equal to g to the power of a times e0. And it's kind of funny, at the end of the day, none of these k parties is actually going to know a, but sort of collectively, they unconsciously know a, or they can prove that together they have enough information to know a. It's kind of interesting. So the way that it works is as follows. The dealer, who is sort of the person who's setting up the scheme, chooses a random polynomial whose constant term is little a. This is the important thing. The constant term has to be the secret. And then what they do is they evaluate it at a bunch of points, these x1 up to xn, and distribute these shares, which are the x value and then the f of x value, to each of the parties. Now, how do these parties prove knowledge? Well, let's just, for the sake of convenience, choose the first k party. What they're going to do is they're going to basically just play the same game, do the same sort of proof of knowledge as from before. So each party chooses a random number, Ri, and constructs this curve. And together they collaborate to construct this curve g to the sum of all the Ri's times e0. And now the challenger is going to choose a challenge, which is either 0 or 1. If the challenge is 0, then as before, each party is going to reveal their secret number. And of course, the challenger sees this and they can say, okay, I'll add up all these secret numbers, apply the appropriate power of g, and check if I get the correct thing. If instead b is equal to 1, then the parties are going to reveal Ri, but minus this, what I'm going to call an interpolation term. And the reason that you want to do this is because if you now add up all of these SIs, you're going to get the sum of the RIs like before, and then it's going to be minus f of 0. from the interpolation formula on the previous slide. So now it's going to be, so the sum of the SIs is the sum of the RIs minus A. And so if you apply this now to EA, the A's cancel and you get ER. So this somehow convinces, this will convince the challenger that collectively this group of K people knows the secret A. Oh, that's it. That's really all there is to it. You apply the Fiat-Shamir transform to this thing, maybe with slight modifications, and this gives you an isogeny-based threshold signature from an isogeny-based threshold proof of knowledge. So now let's talk about Calamari. And Calamari is isogeny-based ring signatures, and then you can also make it linkable. And now the quite brilliant idea behind Calamari is that you can modify the zero knowledge proof from before, which is used in a paper called CSI Fish. I think it's pronounced C Fish. I don't know. And you transform it from a proof of knowledge into what I call a proof of or knowledge. And what do I mean by this? So basically, you imagine there are many instances where you might want to be proving knowledge. There's E1, which is G to the A1 times E. There's E2, which is G to the A2 times E, and so on, up to En, which is G to the AN times E. So there are many instances of this proof of knowledge. And what you can do is you can prove that you know one of these A's, but without revealing which A you know. So you say, okay, I know one of these things, but I'm not going to tell you which one I know, but you're still going to believe me that I know one of them. And so, very naturally, you can think of this as being a ring proof of knowledge. I don't know that this is a thing that you would formally write down in the paper, but certainly intuitively, it's like a ring signature, but for proofs of knowledge. So how does it work? It's actually fairly straightforward. So if you want to prove knowledge of AK, the prover is going to pick a bunch of random numbers, R1 up to Rn, and they're going to use these basically like in a separate commitment for each of the curves E1 up to En, which are themselves related to some base curve E by these exponents A1 up to An. And you're going to apply G to the R1 times E1 and so on, G to the Rn times En, and use these as commitments. Now, the important thing is you're going to send these in a random order. So the verifier doesn't know which curves are related to which commitments. Which public curves from the previous slide are related to which commitments X. Verifier, as usual, chooses a challenge. And then if the challenge is 0, again, as always, when the challenge is 0, the prover is going to reveal their sort of random information that they've chosen, because this is going to let the verifier check that they're playing the game correctly. The other more interesting case is when the challenge is 1, the prover is going to reveal RK, so the kth random value, plus AK, where here AK is the actual value that the prover knows. So how's that going to work? Now, in the event that B is 0, all the verifier is going to do is check that if you apply the R's to the base curve, you should get the I just want to correct an error on an earlier part. So these E1s up to En here, they should all just be E. Anyway, so with that in mind, you check that if you apply G to the R1 times E, G to the R2 times E, and so on, this should yield the commitments, of course, because that's how the commitments are defined if you correct for the typo. If instead B is equal to 1, you instead check that G to the S times E is sorry, this is a second typo. You instead check that some G to the S times one of the commitments is one of the commitments from the previous slide. So this would be like an A in a random, you do something in a random order. Sorry, I just, there is an error, there's a slight error here, but the point is you apply this S to all of the commitments. And the idea is that because you don't know in what order they were sent to you, you can't relate it to the order of the commitments on this, the order of the public things on this slide. So all you're convinced of is that the adversary, is that the prover knows one of these secrets A, but not which secret they know. So I'm sorry about that, but that's the principle. And then of course you just apply the Fiat-Shamir transform, and this is going to give you a ring signature. Now, if you want to get linkability, it's actually quite straightforward. The only thing you need to do is add a new global parameter, which I'm calling E prime. And you're going to add to each signature now. So each, you have these signatures from before, which come from this proof of OR knowledge, and you're going to tag them with a pair T comma pi. Now what T is you get T by applying G to the 2AK times E prime. And the 2 is important for sort of technical reasons that allow their proof to go through. And then pi here is an unrelated proof of knowledge that tells you that, hey, the exponent for T is twice the exponent that I proved knowledge of in sigma. And so in signature verification time, you need to verify that pi is a valid proof. And if you want to link two signatures, all you need to do is check that the tags are the same. And as long as the signatures are valid and these proofs pi check out, then the two signatures will have been produced by the same person if and only if the tags are the same. So that's how you know they're linked. And then finally, in the last couple of minutes here, we'll talk about IAS, which is an isogeny adapter signature scheme. So as I say here, the full protocol has some pieces that I think really don't illuminate the underlying idea. So I'm just going to present a simplified protocol here. So the hard relation that we're going to talk about in the simplified protocol is the following. So the witnesses are these exponents y, and then the statements are g to the little y times some base curve E0. And now signatures and pre-signatures will both be, they're going to come from proof of knowledge of some exponent somehow, but they're going to be with respect to different bases. And that's going to let you adapt and extract actually at the end of the day. So the idea is that a signature is going to be a proof of knowledge of this exponent A, such that EA is equal to G to the A times E0. So this signature resembles, well, it doesn't resemble, it's exactly going to be the signature coming from the proof of knowledge, the basic proof of knowledge from Seaside. Now a pre-signature is going to be very much the same thing. It's a proof of knowledge of an exponent, but now instead of S relating E0 to EA, it relates EY to EA, where EY is one of these curves from the hard relation. And now you look at this and you say, okay, S is obviously equal to A minus Y, because S takes you from a curve that already has G to the Y on E0, and so the Y's cancel and gives you G to the A. So S is going to have to be A minus Y, and the signer knows A the signer knows A, and if they choose Y, then of course they're going to know S as well, so they can produce signatures and pre-signatures. So Alice, who wants to execute an atomic swap, she's going to know A because that's like her private key, and she's going to choose Y because that's her role, one of her jobs in the atomic swap scheme. And so that means she's going to know S as well. And what that means in particular, because she knows S, she's going to be able to produce these pre-signatures, which of course is important. Pre-signing is the first step in the atomic swap protocol. So it's very easy to adapt if you know the witness to the statement, because we know the exponents are, they differ by Y. You just add Y to the exponents that you reveal to adapt a pre-signature into a signature. And then extracting is similarly easy. If you see these proofs of knowledge, one is a proof of knowledge for A, and one is a proof of knowledge for S minus A, or sorry, for A minus Y. And of course, you just subtract these two things, and that gives you Y. Now, the complicated aspect of this, and I'm not going to delve into the details because it's quite difficult, or certainly the most difficult part of the protocol, I think, is that the full protocol relies on a proof of what I call AND knowledge. And the proof of AND knowledge is used to keep Alice honest. Remember, I said earlier that it's important to be keeping Alice honest, because if she can cheat, then Bob will authorize the sending of his asset to Alice without Alice having to respond in kind by sending her asset to Bob. And that's exactly what we don't want. So somehow we need to ensure that Alice is keeping honest. And basically, a proof of AND knowledge is, what happens in a proof of AND knowledge is that there are sort of two instances of the proof of knowledge, but now with different base curves E0 and E1. And what the proof of AND knowledge is going to do is prove that that you know the exponent and that it's actually the same for both instances. So somehow this, if Alice can prove this to you, then you believe that the game is being played fairly. And so for pre-signatures, she's going to prove this for base curves EY and ERY. And for signatures, it's going to involve curves E0 and ER, where these are as defined before. And anyway, at the end of the day, of course, you apply the Fiat-Shamir transform yet again, and that's going to take you from what you might call an adapter proof of knowledge or something to an adapter signature scheme. So actually, those are all the schemes that I wanted to talk about in this talk today. So you've seen signature schemes, exotic signature schemes sort of abstractly, and then you've seen isogeny-based instantiations of exotic signatures. And you might be asking, well, if we've instantiated all these things, what research is left to do? And I think there are two main questions that are important to focus on right now, at least in terms of isogeny-based exotic signatures. So the first is that how do we develop isogeny-based exotic signatures of different kinds? So right now, there are no seaside-based blind signatures, no seaside-based multi-signatures, and no seaside-based aggregate signatures. And I haven't defined these in this talk, but these are other kinds of exotic signatures that find uses in blockchain. So it would be very cool to implement these things in an isogeny-based way. And then the other thing is that throughout the last third of the talk, everywhere I was using this proof of exponent knowledge. But the problem with proof of exponent knowledge is that you need to know the structure of the ideal class group. And for those unfamiliar, I mean, computing the structure of the ideal class group is a sub-exponential algorithm. So we're not able to do it for large primes. And in particular, for Seaside, we know the ideal class group for the smallest parameter set, Seaside 512. That's the only one we know the structure of the ideal class group for. And it was an intensive computation that took quite a long time. For Seaside 1024 or Seaside 1792, right now it's not easy. We're nowhere close as far as I understand, unless maybe somebody has been researching this and they know more than I do, and they've got some secret algorithm. But the fact of the matter is, it doesn't seem like we know how to compute the ideal class group fast enough for those. Now, with that said, sort of interestingly, when we develop large-scale quantum computers, there is a polynomial time quantum algorithm for computing the structure of the class group. So actually, some people, it's been said that Seaside is almost, or certain things based on Seaside, like the schemes I mentioned in this talk that require knowledge of the class group, is a post-quantum scheme. And what this means that it's still believed to be secure against quantum computers, but you need a quantum computer to generate your parameter sets. And that's quite interesting. So the schemes in this talk, I mean, you can do something when the class group is unknown, but they really work well when the class group is known. But it's an interesting question. What can be done when the structure of the class group is unknown? So let me just leave you quickly with the references. So Calamari comes in this paper by Ward Bullins, Suichi Katsumata, and Federico Pintore. CSI Fish, this is the basic, the quote-unquote basic proof of knowledge, among other things, is another paper by Ward Bullins, but with Thorsten Klein-Young and Frederick Vercauteren. DeFeo and Meyer, of course, produced threshold signatures, and Tyree, Moreno-Sanchez, and Mafi produced the isogeny adapter signatures. And that's all for me. I'll stop sharing.
Yeah, wow, Jason Legrow, really a great excursion. So I can say that really in a span of this much of time, the thing that you covered, in fact, you've given us a big assignment.
Yes,
Yeah,
I realize there's a lot of material. I hope
yes.
that
Yeah, because
it inspires you to look at these things on your own time.
Yeah, lecture started with, in fact, quantum interactions, newness, qualifying securities. Really, these are, in fact, my brain was struck over there. Then yes, because lots to think. Really, it's a great excursion for us. It's amazing. Now, you know that Jason Legrow, here the maximum participants are the research scholars and the assistant professors from the Department of Mathematics. Now they are searching for the venues. already the day the lecture started, I think so now their brains are filled up with many avenues. And now this is quite tempting because it's leading to the cryptocurrency. Really,
Mhm.
I was fascinated by your lecture. So from the bottom of my heart, as you are younger to me, I think so, my blessings to you and my wishes. And now I request the coordinators to proceed for any question and answer session. Thank you once again, Jason Legrow from my side. Have a nice day.
Yes, you too. It was a great pleasure. Thank you.
Yeah, yes.
Sir, thank you, sir. Any questions from the participants?
So hope Maheswarao garu we are awaiting for you, sir.
Sir, any questions, sir? Maheshwara, sir?
Okay, I have a lot of questions to ask.
Okay, okay.
Oh, very good.
Just you know that I have been working on a seaside, and
Yes.
I'm glad to see that you are all extending this seaside and seesaw. Even Steven's signature, it has been
Yes.
robust of a seaside, right? Sea fish.
Yes. Yes.
Sea
Yes. Sea
fish.
fish. Exactly.
And sea fish. It's a very beautiful talk. Actually, it's I think you.
Oh, well, thank you.
Not many audience are expert in this domain, really. And
Yes, it's hard to find people for sure.
I was enjoying. I was trying to take note on every slide, and you were covering maximum all areas of isogeny. Particularly, you emphasized more on seaside. And you know, I thought to ask one question that not question. Isogeny adapter signature. Have you published this? I think it is a working paper. Have you published it?
Let me quickly look at my slides to see what I put in there. Yeah, it's still just on ePrint, so I haven't been able to find a published version yet, but I imagine it's submitted somewhere very good. It seems like a good paper.
Oh, you released it. I usually I follow on IACR archives.
Yes.
Okay, I haven't seen this paper. Definitely, I will look at after this. Okay.
So yeah. It's I can tell you right now what number it is. It's the year is 2020, and then it's 1345.
Okay. Sure, I will look at that. And then second thing is, when I was at the Stephen, I was trying to attempt on blind signature using Seaside. I was unable to because operators were not allowing, and I made it, but when he questioned, I could not answer. Then I put it aside. After, I don't think so. Do you think that this will allow to design a blind signature on Seaside, because operations are not allowing properly to build it?
Yeah, it's quite difficult. I mean, it's a bit of a touchy topic in isogeny-based cryptography, because there were a couple of schemes that, based on SIDH actually, that claim to be blind signatures, but then the underlying security properties have been attacked. But then there were also flaws in the proof that made it worrisome. So it was, at least from what I've seen, it's a very touchy area in isogeny-based cryptography. But in terms of Seaside, it's not clear at all to me how it would be done.
Yeah.
So
I was struggling to construct a blind signature using Seaside problem, but operations, class group actions are not allowing to, not many flexibility in terms of operations, right? So that's the reason.
Yeah, it's really a problem, right? Because if you sort of look at it from far away, if you don't think too hard, maybe the class group action looks a lot like Diffie-Hellman, right? And the Diffie-Hellman is so versatile. You can do everything with Diffie-Hellman. You can instantiate any protocol you want basically with Diffie-Hellman. But the problem is you don't have a way to combine two curves, and somehow this prevents you from from doing. Yeah, it prevents you from doing like very natural operations that you would do in Diffie-Hellman. You sort of don't have what's called a ring structure in the exponent for this reason. And ring structure in the exponent is exactly what you need in Diffie-Hellman. So it's a real shame. Like it's a beautiful thing, but it's difficult to get a lot of the things you would get with Diffie-Hellman. Now, I will say the one thing that you have that you beyond just this class group action is you also have the twist. And what the twist does is it takes, if you have g to the a times e0, it turns it into g to the minus a times e0.
Yeah.
And the twist has been used in a few papers to accomplish some interesting things. So there's a paper at I can't remember if it was Eurocrypt or AsiaCrypt, but anyway, one of those like big crypto conferences that used the twist to get oblivious transfer from Seaside. It's quite a good paper. I would highly recommend reading it. And I've used it myself to prove security of a version of Seaside where you want to prevent fault attacks. So it's it's a quite it has many applications. So I would recommend, if you're stuck, try applying the twist and see what comes out.
Okay, thank you, Isaac. Second thing so I was talking just it won't be good scheme, but I emailed you that I'm working on a random number generator using Seaside.
Yes, yeah.
It works, but how random it is it truly random or pseudo random? We are not, so definitely it is pseudo random. I sent
these proofs for pseudo-random number generators, they're so difficult, and I mean the standards are so high for what you want them to accomplish. It's a tough field.
yeah. So I thought to work out on that because it's working, but we are not sure how to test it.
Right.
So if you go to NIST standardization process, there are 15 tests we need to compare it. How better it is. We should go through all 15 tests, but it is very difficult to publish after that without comparing. Yeah, so very beautiful talk. I enjoy really. So we are talking about, I think we can have a lot of applications soon on isogeny-based applications in blockchain technology. But as you mentioned, that still we have a lot of issues in terms of efficiency, other, even these guys have come up with the NBOT has come up with a faulty attack on isogeny as well. These are the issues. Maybe it will prevent some level of use in practice.
In some sense, it's a little disappointing because you look at isogenies and think, it has so many problems. It has so many problems. I can't use, it's slow. It's relatively slow. It has these fault attacks. Like it's relatively new. Maybe you think it's unproven. But if you look at it sort of conversely, it's like, well, there's lots of things to work on. So there's lots of questions that we we answer.
Yeah. Definitely, I would like to continue because I was disappointed when I was there. I was disappointed, but I want to carry further after seeing your talk. A lot more signatures coming through isogeny. So still, we don't have any practical isogeny signature here. Am I right?
Right. Exactly. And especially with Seaside, I mean, the security of Seaside has been really brought into question because of these sub-exponential attacks. And if you look at the recent papers discussing, they call it scaled Seaside. It was only published, I think, online a few weeks ago. It was published on ePrint a while ago, but it was only really published like a few weeks ago. And the parameters they're using are huge. The primes are like 8,000 bits or something. It's like, oh man, we really need to improve.
Okay, thank you. Very nice talk. I enjoyed really since beginning. I have been taking notes.
Yeah.
Perhaps I will talk later.
Yeah, of course.
Let others follow.
If I had known people wanted to take notes, maybe I would have gone slower, but I wanted to get everything in there.
It's okay.
Good materials.
It's okay. You're not giving lecture. You're giving talk, right? So at least I can see the gaps where the research problems. That's what I was trying to take. I could take all the research problems.
I'm so glad it was helpful.
Right.
Thank you, Maheshwara sir. Any questions from the participants? Any questions? Okay, thank you, sir. You are giving us an overview of isogeny-based esoteric signatures and the thrust area of their applications to blockchain. Thank you, sir. And this session was really informative, and to the participants and young researchers, once again, thank you very much for your wonderful lecture, sir. Thank you, sir.
Thank you.
Thank you, Jason Legrow, sir. Thank you very much for accepting our invitation and here.
Once again, thank you, Jason Legrow, for your wonderful session.
Jason is a Professor Chandrasekharan. He is based at Vizag. It is a port city of Andhra Pradesh. And another one is Shiva Reddy, who is a co-coordinator. the coordinator is Dr. Swami. Is not appearing on the screen, but so you might have, yeah, he is the one.
Nice, sir. I'm here only.
So this is one of the private universities in India, and it has
I see.
3 campuses in 3 main cities. One is Vizag, that is a main campus. Another one is Hyderabad, it is a IT city. Another one is Bangalore, it is electronic city. You are familiar, green city. So these are all IT cities. So
Right.
and this is the one of the best private universities in AP. And
Well, I'm
South
quite
India.
honored to have had the opportunity to speak here. It was quite flattering.
All right. Yeah. Thank you for accepting and
Yeah,
immediately
of course.
responded. And he timely responded. I must say thanks even to Lucas. I don't know directly you, but when Lucas proposed your name, I said, Isogeny, I'm very happy. I said, very advanced topic. We are happy to see. That's why I did not choose even my topic. When you referred that you are going to isogeny and signatures, when Enboth said that I'm going to talk on isogeny introduction part, then I immediately have chosen that let me give introduction part of elliptic curves, then on quantum mechanics.
Yes.
So I have chosen, and that's why I set my talk before you two guys. So that is the reason. So thank you.
Yes, that's a very good decision. It worked quite well. They came in a good season.
Maheswara sir, you laid a strong foundation to our participants.
Pardon, sir?
You laid a strong foundation to our participants yesterday by explaining the elliptical cryptography from the beginning.
No, thank you. That's the reason I have chosen.
Yes.
I have chosen because of these 2 talks.
Yeah.
Otherwise, a lot of
that was a good decision. Yeah.
Yeah.
So for the both experts, I have a small doubt how these fuzzy commitments are working on this. Fuzzy commitment schemes.
Fuzzy extraction and
No, fuzzy commitment schemes.
Oh.
Yeah.
I don't know anything about that. I do know people who worked on related things, but
generally,
not.
See, let me give sir. Just I am also not expert in fuzzy commitment.
Yes.
Usually,
anyhow.
Just a minute.
Yeah, Maheswara sir, still the schedule is young.
Okay, they use in for malware analysis, not for.
Okay. Right.
Malware analysis.
Right.
Yeah.
So I expect you, Jason Legrow, will be grateful to you if you attend to our other sessions also. And thank you very much from my side.
Thank you.
Of course.
And bye from my side.
Sign off.
Have a nice day.
Bye-bye. Jason sir, bye sir. Thank you for accepting our invitation and delivering lectures. Thank you very much, sir.
Of course. Thank you all for attending.
Thank you, Maheshwara sir. Thank you, sir. Thank you for providing such excellent personalities for my FPP. Thank you very much, sir.
Thank you. With pleasure. All the time people are there for helping. Right. Thank you.
Thanks.
Right. Thank you, Jason. Right. What time next session, Swami? Immediately.
Now I request all the participants to take the short break and rejoin again at 11:30 a.m. using the same Zoom link. For 8th session, Mr. S. Durga Prasad, Geetam, Hyderabad campus. Thank you. Once again, thank you very much, Sir Jason, sir. Thank you, sir.
Of course, it was all my pleasure. Thank you very much. Goodbye.
Bye.
Yeah. So Chandrasekhar sir.
Maleswara, మీరు తెలుగు మాట్లాడతారా?
తెలుగునండి. నేను పుట్టింది నెల్లూరు.
ఓకే.
చదివింది అనంతపురం, హైయర్ ఎడ్యుకేషన్ అనంతపూరు.
ఓకే.
అప్ టు అండర్ గ్రాడ్యుయేషన్ నెల్లూరు డిస్ట్రిక్ట్. సెటిల్ ఇన్ హైదరాబాద్.
ఓకే. అది మీరు పిహెచ్డి అది ఎక్కడ చేశారు? లైక్ పిహెచ్డి? ఎస్కే యూనివర్సిటీ.
శ్రీలక్ష్మి గారు నేను సేమ్ బ్యాచ్.
ఓహో, మీది ఆల్జిబ్రా అండి రీసెర్చ్ ఏరియా?
PhD by algebra. Later I switched.
సో మా ఆల్జీబ్రా వాళ్ళందరినీ కూడా మీరు ఏదో దేశం పంపించాలి మాకు ఇలాగ మీ వర్క్స్ బాగున్నాయి.
నేను అంటే స్విచ్ ఆల్మోస్ట్ 13 years అయింది నేను క్రిప్టో
స్విచ్ అయిపోయి
అప్పుడే స్విచ్ అయిపోయింది.
స్టూడెంట్ ఆఫ్
Suvarna madam student.
ఓకే ఓకే ఓకే
సో ఆల్మోస్ట్ 14 years అయింది స్విచ్ అయిపోయి.
ఓకే
అందుకని ఇట్లా వెళ్ళిపోయాను.
సార్ మీ మొబైల్ నెంబర్ నేను తీసుకుంటాను సార్.
షూర్ నేను మీ నెంబర్ ఇవ్వండి, నేను వాట్సాప్ స్వామి కార్డు ఉందిలే నా వాట్సాప్ నెంబర్.
అదే నేను స్వామి పంపిస్తాను, మనం ఇంటరాక్ట్ అవుతాం సార్ తర్వాత. మేబీ దిస్ నాట్ ద రైట్ ప్లాట్ఫామ్. ఓకే రైట్ సార్ ఐ విల్ బి బ్యాక్ ఇన్ 15 minutes.
Okay, thank you sir.
Yeah, thank you Sivareddy garu.
Thank you sir. Thank you sir.
Thank you
Maheshwara sir. Thank you Chandrasekhar sir.
Thank you
Chandrasekhar sir, small information sir.
Cheppandi.
In this FDP, participants are from mathematics as well as computer science also sir.
Fine.
Okay sir.
Fine. అలాగే మాస్టర్.
Okay, thank you sir.
సార్ ఓకే నేను మళ్ళీ 11:15 జాయిన్ అవుతాను సార్.
Okay.
Thank you sir.
Thank you sir. Thank you all.